Okay, we continue, and our next presentation will be given by Helmut Simonis and L.Quesada, and they both work for Insight Center in Ireland. And it so happens that I used to be part of this when it was 4C Center, one of the largest in constraint programming, and I know both of them for many years. And they usually try through simple problems present much more deeper concept. And probably today it would be no exceptions. Okay, Helmut, go ahead.
Right, thank you very much. Yeah, welcome to this presentation. I'm currently in China, so I'm a little bit in the wrong time zone for this, but okay, we'll try. Okay, so we are going to talk about Sudoku variant puzzles, and I'll explain what that is. One thing which is interesting here is that we're trying to show how expressive constraint programming can be. We are handling something like 250, I think, at the moment, different constraints for these Sudoku variants. We're interested in doing propagation and not search. We're not trying to just solve the puzzle. We're trying to help people in solving the puzzle as a hobby. And for that, we're using an off-the-shelf constraint solver called Choco from France. Basically, the human interacts with the system with the user interface and by stating additional constraints. This works reasonably well. We have actually are able to solve 97% of the Sudoku puzzles from the Grand Prix, the World Championship of Sudoku. It's a human-only competition, so we can't participate with our solver, but we would win, I think. So the task here is to help humans to enjoy the puzzles. We are not trying to replace the humans. Nobody is trying to give us a lot of money if we can solve the puzzles faster than anybody else. It's a tool that will help a user to enjoy Sudoku variants. Okay, just a word from our background. Jacob said Insight. Well, okay, this was until the end of June. We are now in a follow-on project called RIN AI, which is the same national project on artificial intelligence. It has been renamed because our funding agency likes to rename things, and they're giving us the money, so yeah, we have to live with that. Okay. Why did we actually do this work on Sudoku? Well, 21 years ago, I actually wrote a paper on Sudoku as a constraint problem for a workshop in Spain. And that has become one of my most popular papers. It has over 300 citations on Google Scholar. So it's an interesting thing to see that people are interested in understanding how the technology works for these type of puzzles. And what we try to achieve here is now the same thing for Sudoku variants. And what's the problem? Here we have an example. It's called Second Breakfast by 99% Sneaky. So this is from the web. And what we have here is our grid with some cryptic annotations, lines and characters and so on. I'll explain that in a moment. This is the user interface of our application, and we have a grid here. We have the rules that apply to the specific puzzle, and we have here some actions that the user can work on. He can ask to just solve the puzzle, or to find the propagation, or to step forward and backwards in the puzzle. Okay, so what's this all about? Well, we have a regular Sudoku, and you're probably familiar with that, where in the grid, the values in every row, column, and 3x3 block must be pairwise different. So this is what's called an all different constraint for each of those elements. The numbers in the cells define the value that we're using. So if we have to fill in numbers from 1 to 9 in a 9x9 grid. Every puzzle has exactly one solution. This is a constraint that's imposed so that people can actually solve the puzzle in a unique way. And we don't want to do search. We don't want to guess values. We want to deduce the values. So this should be done by reasoning. And sometimes people say, oh, you are not allowed to do case analysis either. You basically have to do the reasoning without making any choices. So what do the constraints mean? Well, here, for example, we have a V between two cells. It says the sum of the two connected cells must be equal to 5. And yeah, so here it's 3 and 2. Same with x's, so they sum to 10. Here, the black dot means it's one value is double the other. The white dot means it's they're consecutive. Either way, we have a quad constraint where it says here we have values 6 and 7 in the circle. It means that these values 6 and 7 must occur in the 4 neighboring cells. We have an arrow constraint where it says the value in the bulb here must be equal to the sum of the cells. We have a German whisper line. Don't ask me where these names come from. This is the terminology that the people in the community use. Two connected cells must differ by at least 5. We have a Renban line, which this is Japanese, which says that the values on the line must form a consecutive set of integers. A fortress line, which says a fortress point, it means this cell must be greater than any of the orthogonally connected cells. The cage says that the cells in the cage must sum to the value which is given as a hint. And you see there are lots of variations, and we have part of our work is coming up with a morphology or an ontology of the Sudoku constraints, and we have different types here. I don't want to go into too much detail there. We have a paper on this if you want to understand this in more detail, but it means that we understand the type of structure that we can find in the constraints and basically use that to add new constraints to the system as required. There's a lot of work on regular Sudoku. Everybody has written a paper on how to solve this with their favorite tool, with CP, with integer programming, with SAT, with local search. Most of these require search as to find the solution. There are some papers in user modeling and supporting a human solver. And in fact, there was a paper by Bruce Silver at DecisionCAMP 24 on a DMN approach, a rule-based approach to solve Sudoku. There are very few papers that actually look at Sudoku variants and combination of Sudoku variants. And yeah, if you want to get more details of the related work, in our paper, we have the bibliography, which has quite a few entries there. So what is our tool? It's written in Java, handwritten, I have to say. So it's something like 100,000 lines of code, but 90,000 of those are generated by an application framework that we have developed for other decision support problems so that we can reuse. And we have something like 4,500 lines of the individual constraints. So we are writing handwritten code, and we can discuss that, why I think this is the right thing to do. We're using the Shoko solver, which is itself written in Java and open source, and allows us to do propagation-only reasoning, so it does not automatically start search if it can't find a solution. And overall, the system is the standard kind of architecture where we have an object model and then a constraint model, and this model is passed to the solver that objects the constraint model, and the user interface with the user interface, and then the user interface also tells the constraints of what to do. We have defined a JSON format for these variant constraints because there doesn't exist an interchange format for Sudoku variant that is generally accepted. Okay, so what's constraint programming? Okay, it's important. IBM says so. It's a declarative framework where we're describing things in terms of variables, in terms of constraints. And we do constraint propagation, where we remove inconsistent values from variables. We detect failure if constraints cannot be satisfied. And typically every constraint acts on their own, and they only interact with each other by shared variables. Normally this is incomplete and we have to do search, but not for the Sudoku case, because there is only one solution and we only want to do propagation. We don't want to do search. Yeah, this is a way of conceptualizing this. Basically, constraint programming is like making this sculpture. We start with a block of stone and we're removing all the pieces that are not part of the sculpture, and we end up with this beautiful sculpture there of the pharaoh. In constraint programming, we start with an unstructured search space and we remove inconsistent values until we actually come up with a solution that is satisfying all of our constraints. Okay, so modeling, how do we actually model this in the Sudoku in our system? Well, we have a matrix, an n by n matrix of domain variables, and each of those variables ranges from 1 to n. And we have the standard irregular Sudoku constraints that for every row, column, and block, we have an all different constraint, which says that pairwise these sets of variables must be different from each other. We now do propagation, so we only remove inconsistent values, but we are not forcing a search in the system. We leave that to the user. And then we need basically propagators for all the variant constraints. And this is basically the challenge. We now have 200 of these variant constraints that occur in public available puzzles. How do we actually write them down in our constraint programming language? And for that, we have multiple choices. We have global constraints inside the system, like the all different constraint, which express a global condition that holds over a set of variables. We can also express things as a conjunction of either basic or global constraints, or as a disjunction of basic constraints. And these are basically ways of writing logical formula. One way that we can make our propagators more efficient is we can turn them into tables. And tables are very important in constraint programming, the same way that they are important in decision rules. We are basically describing all possible tuples that satisfy a constraint. And then we have a table constraint mechanism that looks at those tuples and does all the reasoning that's possible to extract from that constraint. And this is quite powerful and can still work on a large set of tuples. So even if we have a few million entries in our table, this is still working in milliseconds. So the core of the Sudoku is, of course, the all different constraint. And this goes back to Laurier in 78 and Regin in 94. Regin was the person describing the first algorithm to extract all the information from an individual constraint. We have to note that while we can extract all information from a single all different constraint, if we have multiple all different constraints that interact, that share variables, like we have a row and a column, then this is no longer a simple problem. This is a hard problem on its own. We can approximate the interaction of the rows, columns, and blocks. And this is actually the topic of the paper I wrote in 2005. But we are not going to do that in this particular solver. We are replacing this with something else. And here we have an example constraint, and we're thinking on how can we model this. So we have the Ranban constraint, an example here. So we're saying that on each of those lines must form a consecutive a set of or distinct integers. They can be in any order, so they don't have to be sorted. How do we actually model that? Well, we have three ways of doing this. There actually is a global constraint called all different consecutive values that would actually encode this perfectly, but it's not available in Shoko. consistent, this is actually does all the work that's possible. You can express the random constraint as well as extracting the minimum and the maximum of a set of variables, and then saying that the difference between the maximum and minimum is just the total size of your set minus one. If that holds and you have an all different constraint on these as well, then you're getting the expression of the random constraint, but it's not domain consistent. You can turn this into a table constraint, and the number of tuples increases. If you have a random constraint with 2 values, you need 16 tuples. But if you have 8 values, you need 80,000 tuples. So we are automatically generating these tuples. The user doesn't have to write them by hand. And this type of constraints is available basically in every constraint system, in every CP system, and it's domain consistent, so it extracts all the information. And another constraint would be the constraint of the greatest line, which is another line constraint here, which says the largest value on the line is greater than the sum of any other two cells on the line. And you have to start thinking on how to express this. And it's not obvious how to model this, but we can actually use some global constraint. We have a sort global constraint, which says the sort of X and Y is that the collection Y is a sorted collection of the input collection X. If you actually try to write this with binary primitive constraints, this becomes quite tedious. But if we then want to express the greatest line, we just introduce our sort constraint, and we have our variables that are now sorted, and we're saying that the x, dy n, the largest value, is greater than dy n minus 1 plus dy n minus 2. And that satisfies the condition that we had and does the necessary propagation. Another example, and again a more complicated case, is the 10 line, which says a line can be partitioned into non-overlapping segments, which each add up to 10. And again, it's not obvious how to model this, and we can use a regular constraint. This is a finite automaton, so you express the constraint reasoning based on a finite machine, finite state machine, and that's a technique which has been around for 20 years. And basically you're counting up to 10, and whenever you reach 10, you reset to 0. And this way you can have multiple non-overlapping segments that each add up to 10. Again, quite a concise way of writing down this constraint. You have another type of constraint. This is a parity sum constraint, which says we have a grid here and we have some hints outside. And the constraint says that the value outside here is equal to the sum of the cells in the direction where we are starting from. So in this case, for the 12 in this column, up to the first change of the parity. So here we're starting with 1 and 5, they're odd, and then we're changing to an even number 6, and these add up to 12. That's what the constraint says. And then we have another statement saying that if we have a single cell here, a 3 outside, for example, can also be just a single cell with a 3. Now, how do we express that? We express that with a disjunction of cases, and we're writing this as basically this set of formulas. So for every of these variant constraints, we have to come up with our model, how we actually want to implement that constraint so that it does the necessary reasoning. So some of these things express the constraint correctly, but are not very performant in terms of propagation. And what we can do in that case is what's called tuplification, where we basically take all the solutions of the constraint that we have defined and turn them into a table. And then that table, every row of the table is one solution. Altogether, they describe all solutions, and that makes a very powerful constraint. Now, this doesn't always work in a very compact way. So for some constraints, for example, a magic square constraint, even though it has 99 variables, there are only 41 possible magic squares. For the between constraint, I didn't explain this, but just as an example, for 9 variables, we have over 3 million possible tuples. Our system doesn't care. The constraint solver can deal with this easily enough. Okay. We also have the possibility to add constraints to the problem manually. And this is basically happening when the constraints that we already have are not enough to find a solution. And then the user basically wants to interact with the system and helps to find a solution. Very often you would just say, okay, fix a value or remove a value from the domain of a variable, but we can actually create more complicated constraints and add them to the system on the fly as part of the interaction with the user interface. And we have things like saying that we have a set of variables and they must take their values from a set of possible values, or a set of variables must contain a set of values or must not contain a set of values. Or we have 2 sets of variables and these must be the same values, or they must be the same pairwise of values, or a set of variables must all be equal, or again, they must be all different from each other. These are constraints that occur in the manual solution process that we observed in the internet videos where people solve these puzzles as basically entertainment for the masses. And we see that very often these type of constraints are used to come up with a solution more quickly. And this is how you would do how you would add a constraint. So here we have our puzzle that we had described. You see, if there is a number here in the cell, this is the value that the system has chosen. If you have lots of small little numbers, these are the possible values which are still left in the domain. And this is the result of the initial propagation of our system. So it hasn't come up with a solution. And we now basically want to help the system. And if we look at this arrow constraint, we can say that these 2 variables, one of them must contain a 3. And we're basically clicking on these 2 cells, defining a group. We're saying that we're looking at the value 3 and then say that these variables must contain the value 3. So this is a disjunction. This does not initially propagate does not affect these variables itself. But what it can do in this case is it will remove the value 3 from all these variables here on the right. Because if one of those cells contains a 3, then none of these cells here on the right can contain a 3, because every line can contain or must contain exactly 1 3. So if we do this, we are getting more propagation, and we are basically seeing that, okay, we have eliminated a lot of variables and we have decided a lot of values. So the red values we have actually eliminated in the last reasoning step. We have found a few more fixed values, and now we have to do something more. And in fact, we can add another constraint. Here, if we think about this, we can see that if this value here is 9, this is a German whisper, so this value had to be then at least 5 values smaller, so it could not be 8 or 9, it must be 3, but then this value had to be at least 8 or 9, this has to be again smaller, 3, and then this value would be a 9, and then we would have 2 9s in the same row. And that's not possible, and therefore we can remove the value 9 from the cell, and this leaves only one value left, the value 2, and then we get more propagation. And if we actually enforce that, remove the value 9, it's indicated by this red circle, we actually find the solution of this puzzle. So we have basically done 2 interactions manually. We have said one of these variables is 3, and we have eliminated this value 9. Now, we could, of course, try and do this by an algorithm, and we could do this by search, but this is part of the fun, at least for me, solving these puzzles, basically trying to come up with a short way of solving the puzzle by adding few of these additional constraints. Okay, so this is how we're actually modeling this, how we're dealing with this, and let's look at some results. And we have 4 classes of benchmarks that we have been using. Sudoku originally, well, there is a US source for this, but it has become popular because of a Japanese puzzle company called Nikoli that has published these Sudoku puzzles for many, many years, and we have some early examples here. We basically use some of those puzzle books to see whether we can solve popular regular Sudokus with our system by propagation alone. So how powerful is our solver? Is it as powerful as an introductory level user that can solve these Nikoli puzzles? There's a second category, and this is the gas puzzles. This is a daily column that appears on the web, where every day they bring up a new problem. It's a group of, I think at the moment, 3 people that alternate presenting puzzles. And you never know what you'll encounter. You may encounter a regular Sudoku, or it may be a completely new puzzle where people have come up with a new rule, and you want to, they are basically asking, with this new rule, can you solve the puzzle? So what we try to learn here is whether our morphology of the constraints is comprehensive enough to basically include all these new puzzles, and can we add these puzzles, these new constraints quickly enough that we can deal with this in a fast way. Here we basically want to see whether our system is generic enough to deal with this large variety of. We have the Sudoku Grand Prix. We are looking at the data from last year, where we're actually comparing against basically the best human speed puzzle solvers. So these are people that are incredibly talented in solving these puzzles very quickly by hand with nothing but paper and pen, no computer, nothing. And even the pen is something considered perhaps, well, definitely not a pencil that you can erase. You have to do this in ink, and you have to solve a lot of puzzles in 90 minutes for every round. And then there is a very popular YouTube channel called Cracking the Cryptic, which is really, really popular with millions of viewers, and very often has really complicated puzzles. And the question is, do we have the right manual constraints? Because there's no way that our automated system can solve these complicated puzzles without doing search. It can solve all of these puzzles if we allow to do search, but not without doing search. So the question is, do we have the right manual constraints to basically mimic what the expert users are showing us on the video channel there? Okay, so what are the results? We have three books here by Nicoli. The first book is from '88, so I've been collecting these things for quite a while. This is easy puzzles. At the time, these were challenging, but nowadays they would be considered very easy. We have the Gekikara Sudokus from 2004. They are more difficult, but they are still not really complicated, but they're intended for human solvers. And what we can see is that, yeah, of these simple puzzles, we solve everything by propagation alone. We can have something like 80% of the puzzles solved by propagation alone for the more complicated category, and then solve all of them if we add some dynamic rules to the system. I didn't talk about that very much, but you will understand that you can write down rules, in which case we deduce something for a given situation that we encounter. In that case, automatically, basically, without human intervention, we are getting 100% of all the puzzles. So our system is strong enough to do these basic kind of Sudokus without human intervention. Now, if we're looking at the gas puzzles, so these are variant Sudokus and of different types. We are evaluating this on all the puzzles from January and February 26, and some more from December. At the time when we wrote this, we had 77 of these puzzles. 69 of them were solved by propagation alone. By adding manual constraints, we could solve all of them. But we had to basically add some manual constraints because our propagation reasoning is not strong enough to deal with these type of puzzles. But we can solve all of them, so they all fit into the morphology that we have described. Then we're looking at the Grand Prix. So this is purely a pen and paper competition for humans. They don't allow computers, they don't allow mobile phones, internet connection or anything. The Grand Prix is run by 8 rounds, organized by different countries, where people basically create puzzles. The best puzzle setters from different countries create these 15 puzzles, basically for every round. And then the human have 90 minutes to solve these 15 puzzles. And this is a real challenge. These are the people that participate in this are really, really good to actually get these solutions. You're getting points for every problem that you solve, and depends on the difficulty of the puzzle. You get additional time points if you solve all the puzzles in less than 90 minutes, and then you get time points based on how many minutes early you finish. And that gives you quite a lot of extra points that you can basically distinguish that some people are faster than other people. Okay, here we have the rounds of these of the competition. Altogether, 112 of the puzzles, 5,600 points that are available overall. Our system solves 109 of these automatically without human intervention, and we are getting 5,400 points, so we are missing 210 points. But we are getting an enormous amount of time points because our solver basically solves these puzzles in seconds, not in minutes. So we are getting a lot of time points for the cases where we solve all the puzzles. But for 3 rounds, we did not solve all the puzzles. We missed out on one. So altogether, we are getting something like 9,000 points. And if we're just taking, if we're just taking the 5,400 points that we achieve without considering the time points, then we would be ranked fifths in the competition when we include the time points for the humans. For the competition, the organizers don't separate the results with and without the time points. We would rank first if we include the time points. What are the problems that we can't solve in the competition? Well, these are variants of the thing which are not regular Sudoku kind of things. Here, this is called a packet problem, where we have regions that count as a single variable but cover multiple cells, and we basically have to include this. This is a regular Sudoku in terms of only using all different constraints, but our user interface and our JSON format doesn't allow this kind of format. This is another variant where, yes, you have rows and columns, but you don't have blocks, and you only have partial information about the blocks. So you first have to identify which are the 9 cell blocks that basically partition this grid, and then fill this in correctly. And we have a third thing, which is the so-called 3D Sudoku, where you have a kind of weird structure of what are rows, columns, and blocks. Again, our format does not allow us to enter this at the moment. Okay, the last example is examples from cracking the cryptic, and we are just looking at the most popular examples on their website. The Magic Square Sudoku in particular is one which has over 10 million views. A lot of the others have over 1 million views as well. And we are looking at how many of the manual constraints we need to solve this. And you see the number actually is quite limited. This is an example. Well, this is the Magic Square. It's by a Dutch designer called Art van der Wetering. It's really famous because it's a Sudoku which has only 4 cells filled in. And normal Sudokus require at least 17 cells to have a unique solution. So what is different here? Well, we have these lines, the blue lines, which say that the diagonals are also all different constraints. You cannot repeat a digit. Sorry? Okay.
Keep going.
Okay. We have a magic square in the center, where basically the cells add up to the same sum for the rows, the columns, and the 3 by 3 diagonals. And we have a knight's move constraint saying that if we have a cell here, a cell which is a knight's move away cannot have the same value. So these are additional disequality constraints. This is the propagation that we get initially. So we can actually determine that, yes, it's a magic square. It must be this magic square. It's the only magic square that will fit with the given hints. And it can deduce some other things, remove some other values, but it stops at this point. And we can now basically add a constraint saying that, okay, this cell here cannot take the value 2, because if it takes the value 2, it will eliminate the value 2 from this cell, but also from this cell and from this cell, because it's a knight's move away. And then we would not have a value 2 in this block, and therefore we would have a failure. So if this is 2, we can't put a 2 into this block. The constraint is not satisfied, and therefore this value cannot be there. And if we add that constraint, we basically find the unique solution. So we have the row constraints, the column constraints, the block constraints. We have our anti-knight constraint. We have the magic square and the 2 diagonals. And all of these constraints together mean this has a unique solution. And we basically had to add 2 additional constraints manually to show that this is the solution. Okay, so this is what we have looked at and we have achieved. Okay, what can we do in the future? Well, there are still more variants that we can consider, and this is a good exercise for us, basically, to see whether our constraint system is powerful enough and expressive enough to write down these constraints. There are some constraints, for example, trying to find a path in the Sudoku grid, which we cannot express with the constraints that we have in Shoko. We need a different constraint solver for that. We'll probably have to write a few constraints ourselves. We can improve the reasoning for some of the constraints, and typically this is caused by some interaction that's missing and some reasoning that we're not doing. We're also looking at hints and explanation. So if a user is stuck, basically help the user to find things and scan perhaps puzzles from the printed image and use some AI to get the solution from there. So this is what an explanation would look like. If we want to see why that has to be this value here, we can identify some of the constraints, some of the cells that basically force this and provide an explanation at the level of user concepts and basically convince the user that, yes, this has to be this value. It cannot be any of the other values. And this is something that Louis and myself are working on at the moment. Okay. So what have we done all together? We have an interactive tool to solve Sudoku variant puzzles. Why is this interesting? Well, it's interesting to check that our constraint system is powerful enough, but it's also interesting because we can teach constraint programming with these puzzles very well, and we can show how to model and how to solve systems. We have over 200 constraints so far, and it's still incomplete. I think altogether we'll probably have something like 350, 400 constraints to get the majority of things. But people are inventing new variants every day. We're using an off-the-shelf constraint solver just to show that this is actually existing technology. We don't have to invent anything new. And we get good results in a variety of benchmark puzzles. The aim here is to help humans solve puzzles and not to solve these things automatically with search and just as a exercise in solving combinatorial puzzles. Nobody is going to pay us for providing solutions to Sudoku puzzles. Somebody may be willing to pay us for having a nice interactive tool and perhaps a tool where we can create puzzles as well. And there's a huge potential for outreach. And in fact, this is what we're doing here. We are basically coming for the decision management community, saying, okay, yeah, this is what constraint programming is able to do. This applies the same technique, the same constraints can be used for many other problems. Jacob was already showing some of the examples in the previous talk. Okay, that's it. And thank you very much. And open for questions.
Okay, thank you very much, Helmut. Do we have questions? Let's see. I'm not sure. James just did not turn. James, you have a question or it's just from previous? No. I just probably can make few comments. First of all, I want to thank you, Helmut. I know that you were in China on business trip and and I just checked, it's almost 2 a.m. in the night, right?
And in fact, we had our banquet before the meeting, so I had to go slow on all the liquor and wine and beer, so to give the talk.
Okay, thank you. And I especially like your comparison of modeling the problem with Sculptor. So it's a kind of decision modeler. Could be first time I can see it could be compared with sculptor, but I also thought that I did not pay attention to similar things what we did. When we added constraints to our rules environment, we started regular debugger, what we always had, business-oriented debugger. And every time when we activate, when we go reach constraint and we post constraint, in this moment we can see how our decision variables domains started to become smaller and smaller and smaller. And you brought this point to ultimate situation. You don't need search. Pure constraint propagation actually solves the problems. And this is a great, could be potentially great answer to what James asked previously for validation, right? If we can get some problems and we have, if we posted constraints, constraints can get an error and some domains could become empty, and constraint propagation could be a very good validation tool for, not for toy problems, but also for real problems, right?
Yes, there is another thing which is quite important. This is ongoing research and something that we're basically discussing here in our meeting in Jilin. You now have the possibility to have validating constraint solvers. So proof logging solvers that whenever they make a decision or when they propagate something, they basically record the decision, and then you can automatically, with proof logging software, show that this was correct and that all the deductions that were made were based on the right assumptions, and there was no shortcut where either because you implemented this incorrectly or because you misunderstood some of the constraints, it basically made a mistake. And this is very, very powerful because it allows us to validate that the constraint solver itself, which is a complicated piece of software, is actually operating correctly. And we are doing this outside the constraint solver itself. So it's an independent validation of the constraint engine. So
very
that's
interesting. Do you have a
really a
reference
new
to
thing.
this article? Do you have a reference? Can you share
Yes,
this
there
on
is
the chat?
work
If you can
by
find it and put on the chat or send me email, I would appreciate this. Any questions? Or we will let Helmut go? No? Okay,
okay.
Helmut,
There is a question there on
there is a question. Go ahead.
yeah. It's not yet in the, it's not open source, it's on GitHub. The intention is to make it open source, but we want to have a proper publication out of this first. So as soon as it's accepted, we will make the code and the examples that actually are not copyrighted material available as open source software.
Okay, thank you. And if you don't mind, I want to take a minute to share a personal story related to Sudoku problems. When my mom was in her late 80s, I introduced her to Sudoku, and she was so happy. And that when she was already 91 or 92, she called me and told, I want to show you I found the way, my own way to solve very complicated what was Sudoku problems. Give me more complex problems. And I told her, Mom, I have solver what resolves this problem, so I'm not in this. But she did it, like you said, without any computer, without anything. And then when she was already almost 94, and she could not hold even pen. And she told me, how can I live without Sudoku? I need to solve my Sudoku. And so I bought her a special pen on the finger, and she still can use it. And then I tried to tell her what you said. Mom, let's try to solve this without any pen in your mind. Okay, so was, for me, it was kind of personal problem related to Sudoku. Anyway, thank you very much, and hopefully to see you on next Decision Camp. Louis, thank you to you too. Bye.
Thank you. Bye.
Thank you, Jacob. I'm definitely very happy to be part of this.
Thank you.